3.
Hello, I'm Ben Howard, and I'm going to be talking about how cryptocurrencies relate to mathematics. A cryptocurrency is a type of online currency that makes use of public key cryptography to encrypt its messages so that you can send safe data back and forth to perform transactions with the money. This money, however, does not act like your ordinary cash. It is more like a share of a stock. Its price is what people perceive it to be. However, with public key cryptography, almost every transaction you make is sent across publicly where anyone can access it. So you may think it's very difficult for you to hide your message and keep it private, but actually it's pretty much just as simple as this. We need to make division hard. So now we're going to be looking at a variant of the Diffie-Hellman key exchange. This is how two people, Bob and Alice, can communicate publicly online without being checked by Eve, our intruder. Now, since we want to explain why we need to make division so difficult, we will assume that Eve cannot divide. Bob and Alice both create a private key, lowercase a and lowercase b, in their attempt to communicate. They also create a public number n, which will be shared across the internet. Anybody can see this number. Eve, for example, sees this number and is trying to intrude on their conversation. Alice will do the computation, little a times n, to create big A, and Bob will do the calculation, little b times n, to create big B. They will then swap these publicly. Now, Alice will take Bob n times little b times little a, and Bob will take n times little a times little b. Since the commutative property applies, these numbers will equal the same secret number. Now, the reason we need to make division so hard is because Eve cannot divide in this example. So if Eve could divide, they could divide a by n to get little a, and the same process for little b. They now have n, little b, and little a, which they can multiply to get this secret number that they would then be able to use to communicate. So this is why we need to make division as hard as possible. So in order to find a way to make division hard, we need to look at some various cases in mathematics in which it's much easier to perform an operation one way than to perform the operation the other. One of those examples is with a matrix. It's very easy to multiply a matrix, but much more difficult to divide that matrix, which means to multiply by its inverse, because you have to calculate that inverse, which is pretty difficult to do. Luckily, every 2x2 matrix forms into what is known as a group. So now we can look at groups. So we will now look at the properties of a group. So the group we will represent as group G has a set of elements A, B, and C, etc., and an operation asterisk. So the first property of the group is that it is closed. So for A asterisk B will be in G for all A or B in G. Second, there exists a single identity, which multiplied by any A in G will give us A. Third, there exists an inverse for each A within G. A times A inverse equals 1 for all A within G. Lastly, the property is associative. So A star B star C will be equal to A star B star C. Also, not all groups are commutative, but if it is commutative, in other words, A star B equals B star A, it is known as an abelian group. So finally, we're going to look at elliptic curves. In general, an elliptic curve is y squared equals x cubed plus ax plus b. For example, y squared equals x cubed minus 3x plus 5, which looks like this nice elliptic curve, which we'll mention later in the video. The rule for elliptic curves is the E equals xy in R2, y squared equals x cubed plus x plus b, but 4a cubed plus 27b squared is not equal to 0, but we have 0, which is our identity, and also known as our point at infinity. It turns out that an elliptic curve is a group. To see this, we will need to define our group operation, a form of addition. Now we're going to look at how to add points on the elliptic curve. Note that P, our point, plus our identity, the point at infinity, will always equal P. Also, a point R plus our inverse minus R will always equal 0. To get our inverse, we simply have to draw a vertical line through the point R and find the point where it matches up on the elliptic curve. This is because our elliptic curve is symmetric about the x-axis. If we want to add 2 points, we can draw them both on the curve, P and Q, draw a line through these points, and it'll meet up with another point, R. However, R is not our solution. We need to draw the vertical line through it and find where it meets up with negative R. This is our solution. So effectively, P plus Q equals minus R. But what if we wanted to add the same point to itself on the curve? Well, we might do that by having our point P and drawing another point nearby called P prime. And then you can draw your line through P and P prime, and you get a point on the curve, but it's not very accurate because there's quite a bit of distance. So you draw a point a little bit closer, P prime prime, and then this comes through, hits a point on the curve, still getting closer but not completely accurate. However, you might notice that this is approaching a limit, which eventually will form a line about right here. We can then draw a line through here, hit a point on the curve, and this is our minus r, our solution. So now we know that P plus P equals minus r. Now, if you wanted to add a point to another point, but that point is tangent on the curve, it's pretty simple to do this because you've noticed it's very similar to this example, except instead of P plus P equals minus r, we have P plus r equals minus P. Now we know how to add points in our elliptic curve group. But what about multiplication and division? First, it's easy to multiply a point in our elliptic curve group by an integer. All we have to do is this. So our integer times our point, and that's just equal to point, dot, 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 plus point, n times. Suppose we have points P and Q in our elliptic curve. Can we find n so that P equals NQ? P equals NQ. If we can, this is something like division. So now we've made division hard, but not hard enough. This is known as the logarithm problem. In order to make division even harder, we're going to use modular arithmetic. As an example, let's talk about mod 5. We say two integers, m and n, are congruent mod 5 if m minus n equals 5 times k, assuming that some integer k. For example, 17 equals 2 mod 5 because 17 minus 2 equals 5 times 3. Now that we know that, notice that every integer is equal to 0, 1, 2, 3, or 4 mod 5. It turns out that this collection of 5 objects is known as a group. In fact, it's something called a finite field. If we want to add two numbers, for example 17 mod 5 and 21 mod 5, we can add them by simply converting both of them to mod 5, which you can do by dividing them by 5 and taking the remainder. 17 divided by 5 is 15 with a remainder of 2, and the same thing gives us 1 for the other one. 2 plus 1 equals 3, which is now our answer. If it was more than 4, we would have to divide it and create the mod 5 again. Now notice that we use 5, but this actually works with any prime number. Okay, now we're going to be looking at elliptic curves with modular arithmetic. The curve we'll be looking at is y squared equals x cubed plus 1, except we're going to do it mod 5. Now I made this entire video before and ran out of time, so I decided to make this table with off camera. So we now know that our coordinates are 0, 1, 0, 4, nothing on the 1, 2, 2, 2, 3, and 4, 0. So these are our points on the elliptic curve of y squared equals x cubed plus 1 mod 5. The general definition of an elliptic curve mod p is the set I'm denoting script E sub p. It includes all points x, y in fp2, where fp is all integers mod p. It is basically the same as a normal elliptic curve, except that it is mod p. It also does include our point at infinity. Just like our original elliptic curve, this elliptic curve, mod p, is a group. Analogous to our addition of points in our original elliptic curve, we can add points in our modular elliptic curve. This means we can multiply by an integer n as before. Recall np equals p plus dot 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 plus p n times. Finally, we return to our original variant of the Diffie-Hellman key exchange. The difference now is that the private keys, A and B, are points on the modular elliptic curve. This means that E would have to solve the logarithm problem for a modular elliptic curve to break this code. Good luck with that.